So in this lecture, I want to look at triacylglyceride catabolism, excuse me, not fatty. I have to be careful when I use that term. So triacylglyceride, and really, so this is catabolism, sure. And it's really fatty acid catabolism or breakdown through beta oxidation is the overall process. So beta oxidation is the overall process. This is really, this in addition to the biosynthesis of fatty acids is really beautiful chemistry that happens within the cell and wonderful challenges that need to be overcome. So let's finish that thought. Now, catabolism is focused on the breakdown of metabolites, these chemical reactions in biology that break down big molecules. Metabolism is sort of all-encompassing, whether it's breakdown or buildup. So biosynthesis is going to be the buildup, catabolism is going to be the breakdown. So we're going to actually break down the fatty acids before we build them up. Okay, so there's like a surface, like an overview of this, and that is the fatty acid beta oxidation pathway. Just really cool because, okay, let's say we've got in our group and we've got, let's draw 4 CH2s out. 2, 3, 4. Now what I want to do is I'm going to go ahead and adduct my fatty acid to CoA as the as the thioester. We've talked about this. We talked about this last time. The free carboxylic acid can react with ATP and then react with to make an acyl phosphate, which then reacts with CoAsh or just CoA with a free SH. The SH displaces the acyl phosphate because acyl phosphates are more reactive than CoA. It's kind of like making an anhydride in organic 2 from an acid chloride. The acid chloride is most reactive. The anhydride is a little bit less reactive. So if you could do some chemistry there. Anyway, we're swapping super reactive for not as super reactive, a little bit more stable, can kind of swing them around, which is what we literally do. Okay, from here, we do a really cool reaction where that's called a desaturation, where we actually subtract 2 hydrogen atoms to make a double bond. And I like desaturation over elimination. And we use a new cofactor called FAD, which goes from FAD to FADH2. We'll look at that here in a second. We're going to have our same molecule, but now we've activated everything so much by not only having the thioester, but also having the site of unsaturation. So we've desaturated or introduced a site of unsaturation in the molecule. And now all of a sudden we have an activated carboxylic acid as the thioester with alpha beta unsaturation. So there's an entire unit in organic 2 towards the end when everybody's like overwhelmed, where we talk about alpha beta unsaturated carbonyls. And it's really exciting because alpha beta unsaturated carbonyls are electrophilic at the beta position. So we could even draw like a resonance structure to help us get within the right mental faculties for this, where we show the positive charge at the beta position and the negative charge on the oxygen atom. And so what this does is this then can react with H2O as a nucleophile. H2O obviously not good enough on its own, but in the presence of an enzyme, it becomes activated enough. So we can add that with some H+ transfer. And we get the beta hydroxy. Look at that. Now we have a beta hydroxy carbonyl. Well, this is the aldol product, and previously we had the aldol condensation product. And so it seems like we should probably just do an aldol condensation overall to give rise to, as we're building up our fatty acid chain. Well, aldol reactions are a little tricky in the cell because, I mean, managing aldehydes on a grand scale is cumbersome. It's a little bit easier to work with the thioesters because they can be attached to enzymes. So instead what we do is we instead of going from the beta hydroxy carbonyl, we both build up and break these things down from the beta keto carboxylic acid derivative. So here we're going in the breakdown process, we're going to take NAD, and it has a plus charge because of the structure. We need some H's on there, so we're going to get to NADH by plucking off the hydrogen that's at the center with the alcohol. That's going to give rise to the beta keto thioester. And here we can actually crack this bond right here between the alpha and the beta positions to make two thioesters. And that's a Retroclayson event. We'll go through that in some detail. And we use CoAsh again, which is just CoA as a free SH. And we get a new CoA thioester plus what's called Acetyl Coa. So this is Acetyl Coa. It's both the final breakdown product and the starting material of the first starting material of fatty acids. And so what we've done is we've done our fatty acid -2. Okay, so -2. Now what do? We're not. You might be thinking, well, how did we really catabolize this thing? Did we really break it down? Yeah, we sort of chopped 2 carbons off of the long fatty acid chain. So what do we do next? We take our fatty acid -2, which is down in the lower left, and we push it through the entire process again, where we first desaturate the alpha and beta positions. We then add water by way of a 1,4 conjugate addition or a Michael addition to make a beta hydroxy, which then gets oxidized to the beta keto, which then gets clipped off by way of a Retroclayson reaction to get a fatty acid -4 plus another molecule of CoA. So we repeat that process over and over again. Now let's go through some of the details, namely the desaturation process. With FAD. So FAD is kind of like NAD, and that it's a nitrogen heterocycle that can either give up or take on hydrogen atoms based on opportunities for aromaticity. Okay, so here is FAD without the 2 hydrogens. We're going to have 3 6-membered rings all in a line. We're going to have nitrogen atoms top and bottom of the middle ring, and then 12 o'clock and like 5 o'clock at the furthest ring. There's a couple methyl groups, and then aromaticity galore here. Now, like caffeine, aromaticity on the nitrogen heterocycle gets to be a little awkward because we've got some carbonyls present that kind of muster things up a little bit. Okay, now this top middle nitrogen is attached to the rest of the molecule, which has like a bunch of like molecular recognition things where we've got ribose, adenine, we've got a diphosphate and ribitol, sugar, just a bunch of stuff to help us like fit in the cell. But this heterocycle is where everything happens. So there's FAD. Now what we can do is we can add 2 H dots, 2 hydrogens to this, and that gets us a structure where we have everything is in the same position, but we've moved some double bonds. Namely, we've moved the double bond that was on the carbon-nitrogen bond from being between the carbon and nitrogen, now being between carbon and carbon. So this was one single bond. Sorry, that's a little hard to see in that first one. Now we've made that into a carbon-carbon double bond by adding a hydrogen here and a hydrogen here. Okay, so that can be 2 H dots or an H plus H minus combo, where we add an H minus on one side and H plus on the other side. You can imagine the source of H plus is abundant, and the H minus is where we really need to, that's that difficult hydrogen to remove. Okay, so we can actually go back and forth between these two species, the FAD H, and it's really FADH2 and FAD. So this all stands for flavin adenine dinucleotide. Let's not worry about that too much. But so it's a different cofactor, nitrogen heterocycle. It can accept like H minus that variety of hydrogen. Okay, so what are we going to do? We are going to take our S-CoA fatty acid. Okay, and we're first going to let a base that's on a glutamic acid amino acid grab the alpha position. Hey, alpha positions, we can remove those. And so this is now the mechanism for desaturation, I should add. We know alpha hydrogens are acidic. Okay, so we're in the enzyme active site, and we're sitting here now without one of our hydrogens. I'm going to put some nice space on top so that I can add my FAD residue. Okay, so negative charge is just sort of sitting there, ready to in the enzyme active site. And now FAD comes along. Now FAD is the one without the hydrogen atoms. Okay, so I have benzene over here with the two methyl groups, nitrogen on top that's connected to a bunch of stuff. Nitrogen down here. Now in this starting one, we've got carbon-nitrogen double bonds, and then carbonyl, nitrogen, carbonyl. Okay. So we're at this position. Now the enzyme, while it's going to steal a hydrogen from our thioester, it's going to provide a hydrogen to our top nitrogen. So remember I said we could add an H dot, a pair of H dots to FAD. We can also add an H plus H minus combination. So here we're going to have the H plus added, and simultaneously the negative charge, this is a funky arrow and it can only happen in this enzyme active site with FAD around. We're going to go over to the beta position and push the H over here off. Okay, so the electrons between the carbon and hydrogen are going to go with the hydrogen. That's awkward. That's why we need all this stuff. Okay, this is all just very, even though we're in an enzyme, this is all very unnatural from an organic chemistry standpoint. All of that didn't make any sense because organic chemistry was originally the chemistry of life, and we're drawing arrows within cells, but whatever. Okay, so we're pushing electrons on the nitrogen up here and up here. That's going to finish the job. We're adding the H minus H plus combination to give us FADH2. You can write FADH2. I'm going to go ahead and draw it because I like getting in the habit of knowing these structures. Start to piece together what these structures are. Okay, so there's FADH2. Now, more importantly, for the pathway of interest, we've introduced our double bond. And once we, as I keep wanting to emphasize, once we introduce that double bond, we're off to the races. Water can add in a lot more easily because it's just a beta position. We need the enzyme to make it work within a cell, but it's not like reactions that are unheard of to us. We then can oxidize the beta hydroxy alcohol to the carbonyl, and that's where I want to pick up with now is skip ahead to the Retroclayson reaction. So in the Retroclayson reaction, what we're doing is we're actually doing a Claisen reaction in reverse. So let's look at a Claisen reaction. What I'm doing in a Claisen reaction is I'm taking some acid, carboxylic acid derivative, and I'm going to react it with an enolate of a carboxylic acid derivative. So here I have an enolate. Here I have an activated carboxylic acid. The arrows are actually quite simple. It looks like an aldol reaction, except on a carboxylic acid reaction. That's all it is. It's an aldol reaction. So this is Claisen reaction, where we take the negative charge down. The alpha position is nucleophilic, adding to the carbonyl carbon to give us a tetrahedral intermediate. That's going to look like this. Now, usually we stop at this tetrahedral intermediate and we say, great, we've done an aldol reaction. But because we're on a carboxylic acid derivative, the negative charge will come down, reform the carbonyl to give rise to a beta keto carboxylic acid derivative. Okay, so all of this is the forward Claisen reaction. What we want to do is the Retroclayson reaction. I feel like I don't need to zoom in that much. Retroclayson reaction. But if I zoom in, then my structures are a little bit more in control. Okay, so we want to do the Retroclayson reaction. So here we're going to take our beta, and I'm going to focus now on the molecules of interest. We're going to add now an S minus attached to CoA, and it could be H plus too, whatever. Sulfurs are fairly acidic, so we can lose that hydrogen and give rise to an S minus. Well, now what that can do is that can kind of come up, come down, come up and add here. That's going to give an interesting tetrahedral intermediate. So the tetrahedral intermediate is from the sulfur adding to the beta position. Now the negative charge comes down, comes over to put the negative charge on a carbon atom that's alpha to the thioester. That's no problem at all. But what also happens is we break a carbon-carbon bond. And it's that breaking that's the Retroclayson reaction. I mean, the overall process is a Retroclayson reaction, but the breaking the carbon-carbon bond is the crazy thing that happens. Okay. So that's what happens in this process to give rise to S-CoA plus our now new fatty acyl CoA-S, fatty acyl thioester. I'm gonna write it this way. So we have a new thioester that can be pumped through the system, but we also have acetyl CoA. Now, acetyl CoA, it turns out, is the starting material for the biosynthesis of fatty acids. So we've broken down our fatty acids, and it turns out that a lot of this leads to ultimately the release of a lot of energy, which is energy sources, right? Fatty acids can be used as energy sources, and a lot of these reactions happen within the cell. Okay, and we make this energetically. Of course, it happens in the cell. The mitochondria of the cell, the powerhouse of the cell. I think I skipped like mitochondria and powerhouse of, which every time I say mitochondria, I always make myself say the powerhouse of the cell. So we're going to do this. We're going to release a bunch of energy, and we're going to make acetyl CoA. And we're going to use this as a starting material for the biosynthesis of fatty acids. But we can't just go in the reverse direction. We can't use the same enzymes and cofactors and all that stuff, take acetyl CoA and just build it up into a fatty acid. We have to do this in a separate compartment because we have to do this in a way that makes this energetically sustainable and energetically feasible, both in the forward direction and the reverse direction. Otherwise, we're going to, otherwise the stuff isn't going to work. So we'll get into that in just a second. But what I want to point out is because we crack everything down to acetyl CoA, animals generally have even numbered fatty acids. And that's because they start with acetyl CoA. And acetyl CoA up here has 2 carbons. So we go 2, we add another 2, 2, 4, 6, 8, blah, 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 blah. It's at 18 and we're like good enough. Okay. So we're going to use these, but plants turn out, they can occasionally incorporate propionyl CoA as a starting material, leading to an odd-numbered fatty acids. So plants can sometimes use, instead of acetyl, they can use propionyl CoA, which looks like this, and now has 3 carbons. And so you can get an odd-numbered fatty acid chain. Okay, so interesting feature, but we're going to assemble these 2 at a time, just like we cracked off 2 at a time in the beta oxidation pathway. So to recap, before we move into that biosynthesis, we took our fatty acid. We ultimately put an oxygen at the beta position. That took desaturation to make the carbon-carbon double bond, the nucleophilic addition at the beta position to put an OH at that beta position. We then oxidized retroclayson. We were 2 carbons shorter than we started. Here we're going to go in pretty much the opposite direction, including going through a forward Claisen reaction. Now, what I hinted at, this is going to happen separate of the mitochondria, so we don't cross wires with our energy-producing catabolism event. So in the biosynthesis, we're going to go in the forward direction in a separate component. Now, interesting factoid about acetyl CoA is a common source of acetyl CoA is carbohydrates. Carbohydrates, which means carbohydrates can be turned into fatty acids. So, you know, back in like the 60s when they're like, hey, if you don't want to consume too much fat, just eat a bunch of sugar. More evidence that was BS. Okay, anyway, back to what we're talking about now. So what we want to do is we want to take acetyl CoA, which has 2 C's, up to long chain fatty acids with even numbers. Okay, so what does that look like? Well, we are going to do everything in reverse. We're going to do Claisen reaction instead of retroclayson first. That's going to assemble the carbon-carbon bond. Then we're going to reduce the beta keto group to an alcohol. Then we're going to eliminate the alcohol to make a carbon-carbon double bond. Then we're going to put 2 hydrogens in to saturate the site of desaturation. So what does that look like? Well, it's outlined in the textbook very nicely, but we're going to take 2 acetyl CoAs. We're going to bifurcate each of these 2. But we're going to tie them together, but we're bifurcating them. First, we are going to do a trans-thioesterification where we just swap the thioester group on one side. And so instead of being attached to CoA, we're now at an acyl carrier protein, which is that thing that's assembled to the enzyme, or at least it transfers us to the sulfur that's on the enzyme. So we do like a thioester musical chairs, let's say that. So now we're at thioester attached to acyl carrier protein, which then gets on the enzyme, which they call the synthase in the book. And that enzyme should have an SH. That's going to release the acyl carrier protein, the ACP. Okay, so now we are on the enzyme. And we can do these things in a controlled fashion. All right, now what's happening to the other acetyl CoA unit? Well, something cool happens. We're actually going to incorporate CO2 by way of bicarbonates. So we're going to add some baking soda, which is like a CO2 equivalent. It's going to take some ATP. So don't think this is going to sort of, take care of our worldwide crisis of CO2. But we convert ATP into ADP, we get some inorganic phosphate, and we generate some H+. Okay, the important thing is, it's all important, I guess. But the thing I want us to pay attention to is our acetyl CoA is now bound to CO2. It's as though we did kind of an aldol reaction on CO2, which we saw in a paper previously. Okay, now we're going to introduce our acyl carrier protein again. So this is going to be musical thioesters. To give us we did it. Okay, so now at this point, we are going to do our forward Claisen reaction. The forward Claisen reaction is going to connect this red carbon to this green carbon with loss of CO2. So again, we're not going to use this as our approach to solving the CO2 crisis, because we use it and then we regenerate it right away. So, but the CO2 minus is going to be critical for the Claisen reaction to work, and that's going to give rise to our beta keto thioester. And I can highlight these carbons again. We've got green here, we've got red here. So it was the alpha position of the negatively charged of the CO2 adduct that adds in a Claisen reaction and releases the S enzyme. Okay, so now we're attached to the gosh, a typo here. We're on the acyl carrier protein. Musical thioesters didn't happen. ACP. Sorry about that. Okay, so now what we're going to do is everything that we did previously, but in reverse. So we are going to reduce this, not with NAD+, but rather NADH. It's the opposite of what NAD+ did. It's going to donate that hydrogen atom. And we'll need some H+ too. Okay, whatever. The H+ is along for the ride, we get it. So that's going to make an OH. We're swinging around with the acyl carrier protein, throwing our thioester everywhere. We are then going to just lose H2O from the alpha position. I'm going to highlight the atoms that get lost. That H in yellow doesn't get installed from the NADH. It just falls off as the alpha hydrogen to give rise to our alpha beta unsaturated thioester, which is now, it turns out, to install the hydrogens back on, we don't need FADH2, we can just use NADH again. And it has a little acid coming along for the ride. It's going to give rise to NAD+. And we are back to the fatty acid thioester. And if you look, we're at 1, 2, 3, 4 carbons. So we did everything we did previously, but in reverse. Okay. So what I think I want to do, there's a lot of cool reactions to talk about here, but I think, and like the addition of CO2 with by way of biotin is just super cool. But I think it's important to focus on the forward Claisen reaction. So let me just find where they talk about that so I can get some enzyme details. Maybe not, I guess. I mean, I guess we went through the arrows, but a little bit. But the forward Claisen reaction looks like this. Really disappointed. Oh, it's just right there. Okay, forward Claisen reaction. All right, so what we do is we take our thioester that's on the enzyme. This is our single unit thioester, and we react that with our 3-carbon thioester, which is the CO2 adduct with an acyl carrier protein. This is actually called malonyl malonyl, and then it's just adducted to ACP. So malonyl comes from malonate, which is a dicarboxylic acid with 3 carbon units. Okay, so what we're going to do is, if we could just simply push some arrows, we're going to lose CO2 through this mechanism. The negative charge is going to come over to form the carbon-oxygen double bond that we need in carbon dioxide. That's going to break the bond between 1 and 2 here, establishing a negative charge at carbon 2, which is the alpha position. I'm going to come down here, push electrons up so I don't break the octet on carbon. That just forms a thioester enolate, CP, which then adds up here in the first step of the Claisen reaction, which is the formation of our carbon-carbon bond. And then the S enzyme is released and picks up a hydrogen from who knows where, and that gives rise to the thing that then gets the beta keto thioester, which then, remember, gets reduced to the alcohol, eliminate water, lose water, hydrogenate, or just add NADH to the alpha beta unsaturated system. And you can think about that beta position as electrophilic to accept H minus, and then we are back to where we started. We did it. We covered the biosynthesis in some detail, at least, of fatty acids. And so at this point, I'm going to end this lecture, and I'll reflect and see if we want to talk more about some of the miscellaneous pathways like the terpene biosynthesis. This stuff's super cool. I just don't want to get too long-winded in this stuff. There's a lot of just super cool stuff. Okay, anyway, you guys have a good one. We'll see you next time.